Hi everyone, and welcome to the video on section 6.4. So this video is going to be about arc length. So arc length is really just one formula that we have to deal with. It does take on what looks like slightly different forms, but if you just think about it in terms of this one formula, it's really not too bad to do any problem you'd come across just with this one formula. So let's look at the formula real quick. It says if a smooth curve, so we got to start talking about everything we see right away, right? So smooth curve here, we're just talking about the graph of something, but it's not necessarily a graph of a function y equals a function of x we're used to. We're thinking of, tons of different stuff. So it could be something like, oh, it's a parabola. It could be something like, oh, it's a parabola, x is a function of y. It could be something where you can't do x as a function of y or y as a function of x. So like something like this. So this I couldn't turn my head and try to do this as a function of y. This is not going to be a function of x because of the vertical line test. It doesn't pass it. So pretty much take a line, draw it somehow in the plane, and the smooth part is make sure you can do the derivative at every point. So it's differentiable in a sense. So that's really it. Just don't do any kind of crazy cusps, don't break the line, stuff like that. So a smooth curve here, it's just a little bit more general than we're used to with a lot of the things we've been doing. Okay, if that has parametric equations, x equals f of t and y equals g of t, for t between a and b, what this is saying is, okay, I can't take, like just as an example, this one, I can't write this as y is a function of x. That is no good. And I can't do anything like x is a function of y. Like I try to redo it like in the previous sections. We were able to do that with the volumes and area. I can't do that. One way we can describe a function like this is instead of trying to describe the whole thing all at once, we say, well, can I at least just get a function for how the x moves? So horizontally, how does this curve move? If I can do that, that's right here. X is a function of some other variable t. I like thinking of this as time. And then separately, I'm going to describe y, the up and down of this curve, as, again, a function of t, but a separate function possibly. So in cases where I can't do y as a function of x, x is a function of y, like this one here, I may be able to describe each coordinate, the up and down and the right and left, individually as a function. And instead of having one function for my picture, I just have two separate functions for it. That's parametric equations. So my favorite example for doing anything with parametric equations, as soon as I see something, parametric equations, I usually like to just use the unit circle. This is my favorite example to just have in my head. So got the unit circle. So that's x squared plus y squared equals 1. Okay, now looking at this, there's no way for me to solve x as a function of y to get the whole circle and y as a function of x to get the whole circle. Okay, I need to do something else here. But parametrically, we actually do know how to do this, and you've seen this before. How about sine squared plus cosine squared equals 1? The parameter t is like our angle, right? I said usually it's time, or like I think of it as time here, but in this case, and we can use theta too if you're more comfortable with that, watch, t equals 0, what happens? I'm right here, right? 0 plus 1 equals 1. Got it, okay. Now, I wrap around. Just let t increase, and it just wraps me around and traces this out. So using that idea, what can I do? I can say, let's let x be cosine t and y be sine t. I have parametric equations for this curve. The x value at every point along this curve is given by cosine, the y value by sine. Parametric. So if you're looking for an example that you might have some connections to, and you're not too comfortable with this idea, go with the unit circle, cosine, sine, where that extra variable is the angle. It's not x, right? This is not an x in here. This is not a y in here. It's this other variable, angle, that's not one of the axes, because this is still xy, right? It's not one of the coordinate axes, so I know that's weird for us defining a function like that. But hopefully it's not too bad to see. You give me an angle. In this case, I'm calling it t. I can give you a point. So you give me an angle t here. Here's a point. It's got an x value, cosine that angle. It's got a y value, sine that angle. And that describes a point on this curve. So something for you to try thinking about. Now, I said there were simplifications or changes to this formula. We can still do arc length in situations like these two. So this was our craziest situation we could get to, but we can do it on these, quote unquote, easier situations. For example, if my curve is y equals f of x, like I can write it like this one as a function of x. So our example here is just x squared, y equals x squared. Well, then this formula inside, which we'll talk about in a second, can simplify down because x as a function of t, it's not. X is just x. That's the variable we're using. So taking the derivative of that, I just get 1, right? Take the derivative of this, I get 1. So this becomes 1. This becomes dy, well, dx, which I can do in here. So this formula, and again we'll talk about in just a second, can simplify in this scenario where you can actually do y as a function of x. And similarly, if you have something like this one, which as you can tell from a couple sections now, doing these parabolas are kind of my go-to functions to think about in each of these situations. But in this case, x is a function of y. Well, go back up to the formula. This would be dx dy. Yep, okay. This would be dy dy. Oh, that's just 1. And there you go. So the formula is the same, but it simplifies down in these special cases where we can go, oh, x is a function of y, or we can go, oh, y is a function of x. So these can simplify down a little bit. It seems like there's 3 formulas, but really there's only 1. Okay, so what is this formula, right? Like, what am I talking about with this formula? So this is the arc length. We are interested in, over some time period or set of angles, like in this scenario, what is the length of the curve that is passed out? So just to continue with this example here, we can do that. Let's zoom in a little bit. I'll zoom in here, just sitting on this. So, okay, I've got my parametric equations for my circle, and I'll rewrite them so we can see them. So here's what I'm interested in. I'm interested in the arc length from, let's do 0, and we're going to do radians, 0 radians to pi over 2 radians. Okay, so that would be this length of my circle. So before we go on, stop and think. You know what this is. This is a circle of radius 1. You know the full circumference of the circle is 2 pi r, 2 pi. I'm only doing a fourth of that. So we know that this length should be 2 pi over 4, which is pi over 2. So just always remember, you can use just thinking about stuff you know to get an idea what these problems should be. So that's the length of this arc. But how would we use calculus to do this? Well, it's a little tough to see this, but I don't think it's too terrible. Let's say we're at 0, or actually let's just pick a t value that gets us like right here. So there's some t angle that gets us here. All right, now what you need to picture is a small increase in t. See the dt here? Just take a tiny step in t. What's that going to do? A tiny step in t is going to push us up the curve that way. We're going to go up that way of the curve. Okay, so all right. Well, I want to do arc length. So what actually changed when I took that small step in t? When I took the small step in t, well, look at the functions. X would change a little bit with respect to the change in t. Y would change a little bit, right? Both x and y will change. So hopefully just thinking about that, it should be not too bad to think I probably need dx dt, and I probably need something with dy dt. So this isn't a formulaic way of getting this. I just want you to be able to look at something like this and think about what's happening, why you have the pieces, right? Like, why would dx dt be in here? Well, if I just nudge t a little bit and go up this circle, move up the circle, I'm definitely going to be moving in x and moving in y. So I need both those. So then you might be like, well, why is the square root and the squared and the added? And hopefully you sit there looking at this and you're kind of like, oh, that looks really familiar, right? I got things squared and added. That kind of seems like the Pythagorean Theorem. A squared plus b squared equals c squared. And I have in the past done stuff like c is equal to a squared plus b squared, all that under the root, when I know the numbers are going to be positive, which they are in this case, because we're talking about length, positive, just like area and volume, positive. So, whoa, this somehow is a formula for c. So the way that you can think about what's happening here is as I push up this curve, I can think of what's happening here as a triangle to approximate it. So I'm going to do a little zoom in to this region right here. So let's say that little tiny region I drew is this. So that's a zoom in. I just zoomed in. I don't have a good way to say that. I could try to draw binoculars, but that would look terrible. So okay, here is the point I was at. That was the t I started at. And I'm just going to nudge t a little bit. And I get to this point. Okay, so how could I think to approximate the distance I just went here, right? And let's zoom in even more. Can we enhance? Enhance. Oh my goodness, look at this enhancing. Okay, we've enhanced to the highest possible resolution. So how could I think to not get this perfectly, but, figure out here, and this hopefully is reminding you of something we've done in the past before, I want to get an idea of how long this curve is. Well, one way to do that would just be to see what the change was between these 2 points, right? Just take a line between these two. So just start here and draw yourself a line between these two. And you can see, I know it's a little tough, but the curve is not going to match my straight line perfectly. That's okay. Now, how long was this line? Well, I've got a line between 2 points. How do I find out how long it was? Well, one way to do that, and be talking about this same stuff, right, would be to go, well, change in x, change in y. If I could get those two things, I could use those and the Pythagorean theorem to get the arc length change. And that's what's happening here. The basics of this is I'm using this idea. The change in x squared, plus the change in y squared will be equal to this change squared. This line, which is not arc length yet, right? But it is going to be something kind of similar. We'll just call that c for now. And that c is an approximation of that little tiny arc length. And guess what? If I make this little nudge in t a little smaller, like instead of going all the way here, I only want a small amount more, I bet that approximation for that little arc length would get better. And so we have that limiting idea of how are we going to be changing as we nudge t just a little bit, because that's inside the integral. How are we going to change? Well, that's just given by this triangle and finding this length. That's an approximation for it. Just like the rectangle was an approximation for area under a curve. Right? It's the same idea, that same limiting idea. So that should be c squared. Oops. So we square root. You could do a little algebra to actually get these pieces out, and it's done in the book. It's not bad to see. Definitely something that you can go through. But we end up with this general formula. And so it's interesting, kind of a neat construction that I would definitely check out. But we're going to spend the rest of this video just going through examples of this. So let's de-enhance, unenhance. One of those two. So let's zoom out now and get ourselves to some problems. So we've got this formula. Let's just use it. Okay. Now the first thing that we're going to do is try to think through what these pictures look like. Now we have Mathematica to do this for us. So just to kind of point that out to you, right down here, you can use parametric plot, give the function, the parametric equation for x and y, and then tell Mathematica what t values you want to go over, and boom, it'll just draw it for you. It's awesome. So you can do that. But, you know, it's also valuable to kind of think through this. So here's a table here where I plug in t's, plug that t into each coordinate function, and then get a point out. So -3 into here gives me 9. So at t equals -3, I need to be at x equals 9. So that's right here. 9. Okay. All right, well, where's my y going to be? Because look, there's two choices, right? So where do I go? Well, plug this t into the function y, and you'll get -3, which puts me here. So this is where I'm at t equals -3. And then what you can do is you can start thinking about, like, okay, what happens? Plug a -2 in. I get to x is 4. That puts me here. That's right, this one. This is x equals 4. And then plug the -2 into here, I'm at -2. So you can see that as t is increasing, -3, -2, I'm moving up the curve this way. And then you could keep going. 0, 0 is 0, and so that puts me here at t equals 0, just to skip ahead a little. So I'm wrapping this way. And as t gets positive, now the x's are going to start increasing again. The y's will increase again. And I end up eventually here as t equals 2, and up here as t equals 3. So I'm going this way as t increases, going up this way and through there. So it's a valuable thing to be able to kind of think through this, right? The other thing that you can do to try to get an idea of, you know, where you should go here is just do x prime. X prime is 2t. Y prime, what's that? 1. Okay, so, you know, I'm at -3. What's going to happen in the x as I start increasing t, going down this? What's going to happen? Well, plug -3 in. That's -6. So that tells me that as t increases, x is moving negative left. Okay, great. So I know I'm going to be going that way. What's the y going to be doing? Well, so let's see. I take the derivative. I get 1. So it doesn't matter what I plug in here. Y is always going to go up by 1 as I increase t. So I'm going up and left. Okay, so I definitely am going this way around the curve. So just kind of a valuable thing to be able to play around with to get an idea what these pictures should look like. But of course, you always have this ability too to graph these things, which is super nice. Okay. And then if you want to find the answer here, Mathematica can do that too. Check this out. Do the integral, x prime t, which is one way to denote a derivative. Just put the prime next to the function x prime t. Throw it in there. There you go. Get your arc length. So -3 to 3, this was the length of the curve in whatever units you picked for your problem. Okay, let's do one by hand. So how do we do this? First thing I do is I figure out which of those forms I need for that equation. So arc length, it was the general one and it was the two simplifieds. Here I clearly have x is some function of t, y is some function of t, and there's no, clear way for me to write this as y is a function of x is a function of y. So then I'm going to just immediately write down arc, well, that's not how you spell arc. Arc length is integral a to b square root, and then I need both of these, dx dt squared plus dy dt squared dt. Okay, so then just fill in the formula. Get your dx dt. Right, you got all the pieces you know, placed in here you need. Now get the pieces. Take the derivative of this, that's 6t. Okay, dy dt. Take the derivative of this, you're going to get 6t squared. Now you can plug this in here, but first let's get a and b. A is 0, b is 1. That's just coming from up here, the t values. Okay, plugging that all in, let's go down here, give ourselves some space. I've got the integral from 0 to 1, square root 6t squared plus 6t squared squared. Don't forget that there's an extra square on these, dt. So, you know, this is just going to end up being some good algebra here. 0 to 1, square root under here. So this would be 36t squared plus 36t to the 4th dt. And this might look pretty bad, but, you know, just trust your algebra, keep going. Integral 0 to 1, square root. I'm going to factor a 36t squared out of this. That gives me a 1 left over plus t squared. Okay. And then look, I've got this thing here. It's all multiplication, which is good. And I can take this out of the root because these are both squared. So that's, watch what happens, 0 to 1 of 6t square root 1 plus t squared dt. Remember, you can take things out of the root as long as you square root them, and this has to be multiplication inside. That's another key component. If it was just 1 plus t squared without this, there's nothing I can just take out. But we're at this point, and then you just have to kick back into your, oh, how do I solve integrals? Well, looking at this, I see a function inside a function, which makes me immediately think, let's try u sub. du is 2t dt. And would you look at that? This is going to work. We've got everything we need. Now this is actually a 6t dt. So what I can do, there's a couple ways to do this, of course, and you can do whichever you're comfortable with, is I'm going to write this as 3 times 2. So that there is a, see the 2t? There is a 2t with a 2t. So we could do the substitution. This is going to be the integral. There's a 3 here. 2t dt becomes du. And then this is the square root of u. Now the bounds, again, this is up to you how you want to do it. Change the bounds, right, to use, or leave them as t's and then just go back. Let's just change the bounds. T equals 0, u equals 1, t equals 1. Again, I'm just plugging in here. U is equal to 2. So this is going to go 1 to 2. Not too bad. Okay. Then we're going to do this antiderivative. Remember, this is just u to the 1/2 algebraically. So then I can do this antiderivative. The 3 stays constant. Add 1, divide. So that's 3/2, but you flip it. U to the 3/2. Okay, from 1 to 2. Got some nice algebraic cancellation. 2 to the 3/2 minus 1 to the 3/2. This is equal to 2 times 2 to the 3/2 minus 1. Okay. And then you could combine this more, that's fine. Or you can leave it, doesn't matter. There you go. Or you could plug it in a calculator and get a decimal approximation too, if you want to get a feel for the size of the number. That's fine too. There we are. Arc length. Boom. Identify. I should use this full, general formula. Get the derivatives of each of these. Figure out the bounds. Plug it all in. Do some algebra. We got a u sub in this case, which is a common, end way to integrate these problems. Solve. All right, let's try another one. So in this one, just even looking at the curve, looking at this being like, oh no, definitely not y is a function of x, vertical line test. Maybe x is a function of y, but then looking over here, it's like, ooh, I don't see a clear way to combine these to get x equals function y, right? That looks like, how do I even do that? So we're going to say, no, I don't think that's going to work. So let's just treat this like we've got the two parametric equations. So this is going to be the integral from -8 to 3. Go a little quicker on this one. Boom, boom. Square root. And now, what do we need? We need dx dt. That's e to the t minus 1, doing this derivative. dy dt is, and then we've got to be careful with this one with the chain rule, right? This is going to be 4/2 e to the t over 2, which is just 2 e to the t over 2. Okay, so that's e to the t minus 1 squared plus 2 e to the t over 2 squared dt. Okie dokie. So let's see what we can do in the algebra here. We're going to have to check it out. Who knows what's going to happen? So this is -8 to 3. All right, now under the square root, we'll make it bigger this time. I've got e to the 2t minus 2e to the t plus 1. That's multiplying this one out, so make sure you're doing that along with me. And then this one is going to be plus 4, and then squaring these is going to be e to the t dt. Okay, let's do some combination. -8. Oh man, not negative infinity. My 8 fell down. -8 to 3. Okay, so I've got square root e to the 2t. These combine to be plus 2e to the t plus 1 dt. Now, you might be looking at this being like, okay, well, I'm just going to stop because I don't know what to do. But don't do that. I'm not going to give you a problem that you can't maneuver some way into something we know how to do. This is something you may have seen before, maybe not, but this is actually quadratic. Pause for dramatic effect. Quadratic in e to the t. Remember, e to the 2t is e to the t squared, right? So this is quadratic. Pretend that e to the t is x. This would be x squared plus 2x plus 1. It's the same formula, just instead of x, it's e to the t. So we know that we can factor this into x plus 1 squared. So we can factor this into e to the t plus 1 squared. If you don't believe it, multiply this out, you're going to get this. I know. Your mind may have just been blown. Maybe not. Maybe you've seen this before. So e to the t plus 1 squared dt. Look at this. Square root, bye-bye. -8 to 3 e to the t plus 1 dt. Okay. So then we can actually just do this out. This is, antiderivative of this is e to the t. Antiderivative of this is t. From -8 to 3. My hand really wants to draw that as negative infinity. I don't know why. Okay, plug 3 in. E to the 3 plus 3 minus e to the -8 plus -8. And plug that into a calculator or leave it as it is. Either way is fine. There you go. We have a number. Boom. So, quick review. I don't want to try to combine this x as a function of y. Let's just leave them as the two parametric equations. Okay, do the derivatives, plug it in, do algebra, do some more algebra. Oh, let's do more algebra. Get to something that we can do the antiderivative of, do it, plug in. There you go. So hopefully it's not too many extra, it's like an integration problem that we have to do. It's just we had to take an extra step or two to get the problem set up. And that's what you'll see happens a lot going forward. But that's it. There's really not too much more in this section other than, you just got to practice some of these, get used to the formula, get used to these algebraic manipulations. That might be the thing that's toughest for some of you. It's just these, like, I'm stuck here. I don't even know what to do. A lot of factoring things out. It's a huge, huge component of this, is trying to factor things so that you can take something out of the square root or just get rid of it completely. So that's what you got to be looking for. So any questions, of course, let me know, and I'll see you in the next video.